All right, welcome to week 68 of Chill Kernel Hacking for Fun. Thank you for joining. I'm just gonna do my basic checks. I think we're live though. What's up? Oh man, test -2. What's up? What's up, Yazaldi? We're gonna kick it back into the positive numbers. But thank you for joining the pre-stream testing, which is negative numbers only. Cool. I think that might be a record for the fastest time someone has posted in the chat. Test 1. Oh man, Afnan's gonna be pissed off that you beat him to the test 1. He might show up later. Cool. Well, thank you for joining. We're going to be working on networking today, just like we've been doing for the last couple months, basically. And I'm feeling pretty good about today. We made a lot of progress last time in terms of the stability of the network driver. Well, more like, not exactly the network driver, but more kind of like the user space components that are in the network stack. And my goal is to get these this test suite passing. Your code should pass the test input test of make grade. So that's the goal. We're going to try to get this test suite passing today, and maybe it's trivial, maybe it's really easy actually, I don't know. Yep. Just taking some time to clean up my various windows going on here. Some Kimu windows, sorry. Last time I was having some technical issues on the stream where it was kind of dropping out, so I'm just keeping an eye on that this time. Hopefully I should be able to, hopefully those problems don't happen this time. Seems like so far I have not seen the chat widget messages working. So it might be time for test 2 actually. So for that chat window seems pretty, chat area seems kind of blank. Okay, just a little bit delayed. Okay. As usual, let's kind of take, why is there so much stuff here? Okay. As usual, let's take stock of what we have here. I haven't worked on this at all since last week. And yeah, a bunch of this stuff actually is from my attempt at speed running something at the very end of last week's stream. I was trying to speed run a bit more reliable way of doing things, which involved a wake up syscall. Yeah, something like this. What I'm realizing is that actually this whole approach was not the right way to do it. So I think I'm probably just going to drop or stash those hunks. Then these are, okay, so basically here's what I'm going to do. I'm going to stage everything I don't want, like this, like this. This is a little bit neutral. This was for debugging last time. Okay, this is the stuff I don't want. So what I'm basically doing is I had a bunch of I had a mixture of changes in my working tree. I had some actual just legitimate changes I've been kind of that I kind of want to have, and then I have this experiment that I was running. I don't want the experiment anymore, so what I'm going to do is I'm going to stage all of the ones I don't want, then I'm just going to stash all these staged changes and just get them out of there. Okay, this slightly confusing. Okay, I also don't want this. I think that's, and this thing is kind of, I don't know why that is there. I'm going to stash this. I think that that's mostly it. So I'm just going to pop over to lazy git and do a stash staged changes. Experiment. Syscall, like wake signal, syscall, syscalls. Oh. Country. Okay, what? How can you not? Okay, that's actually unfortunate. I think that approach is not going to work. I'm going to do the opposite approach then, possibly. I wonder if this is going to work. I'm going to stage all the ones I do want. And then now we're left with kind of the opposite. All the stuff I don't want is in the working tree. Let's try the opposite now. Stash unstaged changes, experimental. Okay, I think that worked. I think it's, for whatever reason, that was simpler to do. Welcome to everyone joining the chat. Hope you're having a nice day. We're just easing into things here. Okay, so now we kind of got that experiment cleaned up and out of there that we don't need. Move everything back here. So this was just this was debugging stuff. I'm not going to get rid of it just yet. This hunk, I will tentatively commit this hunk. Don't enable broadcast. Okay. Word. Okay, I'm gonna come back in here. I think. Let's clean up these tabs and stuff. Let's start fresh. Okay, we actually did need all these yields. What I'm working on is this is the part of the OS that is responsible for calling. It's a user space process, and it's responsible for doing this syscall that calls into the network driver and retrieves data from the driver, and then it forwards that data on to its parent process, which is actually going to handle the data. And we need these yields here because actually there was this race condition where this process would trigger the IPC message, but something was happening where it would kind of go so fast that it would already hit the syscall and actually overwrite the buffer, because there's this shared buffer between the parent process and this helper process. And so we insert a lot of yields to make sure the parent process can get some CPU time to process the packet before this thing comes in and overwrites it again. And there's probably better solutions to this. That's kind of what that experiment was that I was prototyping last time but didn't get to work. And actually, now that I'm thinking about it, the simplest way to solve this in a better way is probably to also use the IPC system, where this process is going to send an IPC message to the parent process. But then the next thing it's going to do is, instead of doing all these yields, we're going to make it wait on an IPC message from the parent. And actually, that's kind of like this, that's already this signaling mechanism that we need. But for the moment, I'm just getting things back into the working state that they were in. Yes. Okay, let's let me remember, we need the grade lab 6 script, and we were running these like tests. Right. And I want to bring up the driver because as I learned, it's actually kind of important that we have more descriptors than this number here, basically, because this is the number of packets that's kind of going to be just like blasted into the OS. And if this number of descriptors is not big enough, we will potentially drop packets if the OS isn't fast enough at processing everything, which I don't really think it is. So for the sake of passing the tests, it's just important that we have enough descriptors available so we can manage this load of packets coming in. Okay, let's run it. So how do I run this? I just run the just run the grade lab 6 thing, right? So now it's running. Okay, cool. So it passed the test. It passed. This right here is all we're doing. It passed the 100 test. Let's just run that a couple more times, just to really have a bit of additional confidence that it's passing the 100 packet test cleanly. And so far, that's looking pretty good. In the past, it would fail non-deterministically, and so that's why I'm running it more than once. But this is looking pretty good. Yeah, this is looking pretty good. All right. So now I would actually be interested to sketch out this IPC message thing I was talking about. This better solution instead of doing all these yields. Just quickly, anything important here? Okay, we did not actually end up using this because we were just using T last time. I will get rid of that. Okay. Yeah, let's sketch out this solution. So what I'm going to do is I'm just going to start coding. So I still am getting used to the IPC system here. So now, so what I will do is I'll bring up the other side of this, the parent process, which is test input.c, which gives a kind of just an example of how to receive an IPC message. So now basically what we want to do is we do an IPC send, and then we do an IPC receive, and the IPC receive you pass, it's like a little bit weird. There's like some output parameters and there's an input parameter. Okay, so I'm going to, in this case, so the IPC system usually is used to transfer a shared memory page between processes, but in this case I don't actually need that. So I'm just going to pass in null here. Yo, what's up, Chandu? What's my word per minute? I have no idea. Probably not that fast. Thanks for joining the Twitch chat, though, by the way. I'm a little bit newer on Twitch. I have more followers on YouTube, but I'm trying to build up, or at least try out Twitch as a streaming platform. Okay, maybe I'm just going to not care about these things, except for maybe this. So so the IPC system can send the shared memory page, but it also just sends integers. And it really does not matter what the message is. For just like I could send a 0 or something, but I'll just make up this fake thing called nsrec_wake. Wake up the input helper process. I don't know, it's just kind of a random thing. So then we can say nsrec_wake. We're going to get rid of these sys yields. And then on this side, we want to add something kind of comparable. So here's the receive. So here's the receive that corresponds to this send. The helper sends over into this receive. The receive returns, has access to a packet data buffer, does whatever processing it needs. In this case, it's a hex dump. And then it's done. And then it basically like does some printing. So here's where we could do IPC send back to the input helper. And I'm just going to copy how it's done here. IPC send is going to go to whom, We're gonna send the NS wake. We're gonna send a null, and I think this argument doesn't matter. Okay. Maybe I'll just do a print here, like woken up input, woken up by test input. And I'll maybe also just add a waiting for test input. Okay. Yeah, so I just have some basic print statements to help me understand this when I run it. Any other obvious bugs that we can see here? We send it over, then we just wait for an IPC message from like anybody, basically. I guess we can also sort of replicate this. We expect that the message only, so we check that the request should be a valid one, not like an error. I don't actually know when it would be negative, but then we check that it's coming from the appropriate process that we expect it to. In this case, it should be coming from this, whatever we receive as an argument. And then lastly, we just check that it's the wake message specifically. That's the one we're looking for. So I'm kind of curious, actually. I'm just going to, yeah. Okay, I'm just going to run the kernel, but not in that test suite environment. I'm just going to run it like more generally. Okay, so now the kernel booted and it's waiting for network data to come in over the network. And so then I have my trusty Python script, which is just going to send 25 UDP packets into the VM, basically, where the OS is running. Let's do that. And let's just see what happens. Okay. Something happened. I think that kind of worked. We see the waiting for test input, woken up by test input. So I mean, we are like, that's happening. And also, maybe this is kind of neat. I guess we're no longer seeing interleaved outputs? Question mark, are we? What's up? What's up, Prithvi? Thanks for joining. Yeah, welcome to the channel if you're new. What's going on here? At a very, very high level, I'm doing some operating system development. What I do on my channel, at least what I have been doing, is I've been working through this like MIT operating systems coursework that's freely available online. And I've just been doing all of the labs for this OS class. And I've been doing this for a bit over a year now, and I'm pretty much almost at the end of the class. The final assignment is to work on some networking stuff for the OS. And specifically today, we are really like kind of hardening and improving the receiving capability of the OS, or of like the networking functionality. And this is involved, earlier I was writing a driver for the network interface card, and that part is done now. And then now that that part's done, there's a few other components that live in user space that I've been working on. And I was debugging some issues with them. We were like dropping packets, unfortunately, and duplicating packets because of some problems that I had, but I debugged those. And now, literally right now, what I'm doing is I'm trying to improve one very specific part of what I was doing last week. In order to fix those bugs that I mentioned, we had this race condition, and in order to fix the race condition, I added a kind of sloppy fix. I added just like a bunch of these calls to yield, and it's just sloppy. It's not a great solution. It's just not great code. So what I'm literally doing right in this moment is I'm trying to improve that. And instead of doing all these yields to make sure that this process gets the execution time that it needs, I'm actually adding coordination between these two processes using an IPC message. And that sort of formalizes their relationship, which is that this process needs to wait until the parent process has processed the packet before this process should continue. So I hope that helps orient you a little bit. I know it's kind of a bit much to just like dive right into like what I'm doing when there's kind of a lot of context that you might not have. All right, stream still seems healthy, hopefully good. Yeah. Okay, so why do I have so many terminal windows? Okay. Anyway, I think this is working. The OS is still waiting here, and if I can probably send some more packets if I just run this again. Yeah. And so it seems pretty stable. It's sitting there. It's accepting my blasts of 125 packets, and actually we're now at an interesting point because the head pointer is now getting kind of close to the end of the ring buffer. The ring buffer is 128 like slots long. And on the next time I do ascend, the head is going to wrap around. So I just want to, that's like an important test point to make sure that works. Hopefully that works. I believe that worked. Okay, so what I've done is I've sketched out my improvement using an IPC message instead of just doing a bunch of yields. And then now the next thing would be to actually test it with the test suite. Dang, how do I? So now we just kind of checked that it's like kind of working. Let's just run the test suite again. I mean, it seems like it was kind of working, so hopefully this should be kind of boring actually. My expectation and hope is that it will just work. Yeah. Afnan, what's up, dude? You unfortunately you got beat out by by Yazalde, but feel free to leave a test 3 if you want. We were doing quite a bit of testing earlier, even some negative number testing. Yeah. Anyway, still glad to see you though. Let's run the test suite. Test 3 then. Okay, that passed the test suite. So I am feeling good about that. Yeah, this still seems pretty stable. This still seems stable. Maybe for people that are kind of new to this topic or that didn't see the past streams, what I can do is I can just demonstrate the failure. If I just remove, if I comment out this code, and then if I comment out this corresponding other caller, I expect the test suite to fail. Let's watch that just out of curiosity. Also, what's up, Baka, for fixed while testing? Test suite passed. Interesting. Well, it's not failing. Okay, there it is. Fine. Okay, cool. Huge relief. Okay, good. It failed. So, so also, what's up? What's up, SciB? What's the link? I got you. There's the. Yeah. So yeah, as you can see, this test failure is non-deterministic, and it actually passed a couple times, but it fails every so often, and it just passed again. So anyway, yeah, so that's what a failure looks like. It's basically saying it. I mean, it's kind of hard to read actually. Unexpected packet. Unexpected packet with this packet 3 thing, missing packet with the packet 2. So what the tests do, all the tests do is they do the exact same thing that my little testing Python script does. It just sends a bunch of UDP packets with this like text data in the packets, and the tests just like check that every single one of these packets comes in. And what we see here is that actually a packet 3 came in, but it came in before the packet 2 came in. And actually what happened was the packet 2 ended up getting dropped because of this race condition, where the helper process was going way too fast, and it sent over packet 2, but for some reason the parent like slowed down for some or didn't get scheduled, and then the helper process already retrieved packet 3 and overwrote the buffer with packet 3, and then by the time the parent actually got to processing the buffer, it had a packet 3 in there, and so that's what it looks like to drop a packet. We just overwrote it before the other person that was interested in reading it was able to. So that's what the failure looks like. So I'm glad we could just demo that. And then, so now let's just, let's bring back the fix. And hopefully that should, it's hard to like actually test whether the fix like truly really is working, but maybe we can try to run it like 10 times or something like that and just see that it's never failing. I mean, it failed like I think on the 4th or 5th time, so last time. So we should yeah, this is looking a bit more solid. So Bach, for send more packets, yeah, what we could try to do a bit more of an intense test where we send a lot of packets. There is one problem with that though. I will explain that in 1 second, but basically, okay, this looks like this. I would say this looks pretty solid to me. It hasn't failed in I don't know, like 10 or 12 runs, so I think we can call that fixed. The problem with basically just cranking up this number way higher is it at some point it's actually going to overwhelm the NIC. It's going to overwhelm the NIC, and that is just going to drop packets. And that's kind of a separate issue. And so if we stay under 128 packets, we are guaranteed to get all of them. But if we actually exceed that number, then basically like currently the OS is not able to process them fast enough, so the NIC is just going to drop them, and so the tests will fail. Yeah, and so I think with all that done, we can bring this back to the original state where it had the 5, 1, and this one. But good question though. Yeah, thanks for asking. Okay, so that is that's running. So I will do a commit now because it's time for that. So I'm going to delete this. I'm going to even delete these. I'm going to delete this. And maybe I will even change these to asserts, because that's kind of what it actually is, assert. Assert whom is equal to assert. Okay. Yeah, so that's just how we're doing our error handling for the moment. We're just doing asserts. Let's just run it one more time. And just one more, just for fun. Just checking the YouTube. We got 18 people in the chat. Awesome. Welcome and hello to everyone in the chat. Okay, so that seems to be working. I think, yeah, so I think we're good to make a commit. What happened? Okay. This remains put, and then this, maybe I'll even delete the comment. So this is what our commit looks like. Fix race condition with IPC message instead of you thing. I'll commit that. Actually, what I will do is I'll also add a comment. After sending the IPC message to the parent, we need to be careful to not enter the next loop iteration too quickly, or we'll overwrite the packet buffer before the parent can process it. Simply adding sys yield here fixes it, but instead use an IPC message for more formal coordination. A coordination, okay. Oh, dang, we needed this one also. Okay, so we're just going to amend all of that into this commit. So now this commit has the comment, this thing, and this new thing. And I think that's as good as time as any to take our first little 20-second break of the day to stand up and stretch and whatever. So I'll be right back. Okay, nice. Cool. So that's great news. We got that fixed. Zardes also using timeout for breaks. Awesome. Another timeout enjoyer. I think I just searched on the App Store for, or just searched in Google or something for it. But yeah, I'm a fan. So what's next? So your code should pass the test input tests of make grade. That's what we just did. To more thoroughly test your networking code, we have provided a daemon called echo serve that sets up an echo server running on port 7 that will echo anything back sent over a TCP connection. Something to start an echo server in one terminal and then connect to it from another terminal, and then make sure that works. Cool. Let's just check out how the echo server looks. So this is actually going to. So first of all, it's going to use TCP actually, and it's going to use the sockets API that is exposed by lightweight IP. So we're using lightweight IP for the network stack here. Okay, and yeah, so this thing actually creates a socket. What probably like binds and accepts? No, like was it bind, listen, and then accept in a loop or something like that? That's how the BSD socket API works. And then accept in a loop, then handle client, and it just happens directly right here, I guess. We read some data, and write it back or something, and close the socket. So we're listening for data, right? So we receive some data sent over the network. And then we send it back, right? But then we check for more data. And then while there's more data to receive, like, we keep trying it, and then if the read call ever returns 0 because there's nothing more to read, we finish handling the connection. Let's try this thing out. So what do we need to do? We do make run echo serve. Like this. Okay. Then make NC7. Whoa. That did something, I think. And it seems. Hello. I'm not quite sure what I'm expecting to see. I actually, Something did not immediately look right to me. Is the echo server really running? Test. What is it? This? I am not sure. Not sure what's going on. Also, what's up, Kedar Codes? Hello, nice to see you again. Also, got the all caps today. Well, this is interesting. This is interesting. What can we do about this? I'm not even sure this thing is even running. So, hello from EchoServe, right? Do we even see that? Waiting? Who prints this message? I suspect something is just like wrong. I think this is, I think this is wrong. For some reason, test input is still running. Oh, wait, I possibly know. I think I actually really need to, so now we're like really using the network server. And by network server, I mean the actual, like, let's see. Net serve, I believe serve.c. This is the main like core of the network server, which we actually haven't used until literally right now. And I had that like commented out because I kind of thought it would mess things up. And actually that's important. So let's run it again. Oh, okay, yeah. So now, all right. So now I think go serve. Fuck. Ooh. So now it's not compiling. IDK, bro, the MIT course took you 60 weeks to complete. How long did you spend each day? I have spent about 2 hours per week working on this, because I will only work on it during my streams, and I only stream for 2 hours a week. So I guess it's taken me approximately 120 hours to do the course. But that's with this kind of weird way of working on it where I can't actually concentrate on it for more than 2 hours, or like work on it for more than 2 hours. There have been a bunch of, like, a couple 3-hour sessions in there, but approximately 120 hours. So we are failing to compile now. That's kind of interesting. Okay. If I comment this out again, does it compile? Oh, hello from EchoServe. Wait, whoa. Okay, so this is what? Hello from EchoServe. But I actually still expect this to fail because the main network server is not running. And that's bad. We need this thing to be there in order for anything else to work. So okay, now I don't really know what was going on there. Now clearly something is happening. So we got the hello from EchoServe, some blah blah blah, open socket trying to bind, bound, blah blah blah. Okay, so good. So this is looking good actually. So now let's connect over netcat, and then we'll type in a bunch of A's to make it easy to maybe see in something. Oh, okay, now I know what the problem is. Now the problem is that in our input helper, we've added this receive, and we like integrated that with the test input process, but we didn't do that with anything else. And actually that's kind of important now. What I'm going to do is I just need to copy this IPC send line somewhere, probably into where actually? So who is reacting to nsrec input? It's literally the network server. I think I need to have this here. But what's the whom? args. Args whom? Okay. If this doesn't work, I'm going to revert this fancy fix and just go back to this like whole yield thing. Let's try it. Let's try it again. Build, run, bound. Client connected. Okay, big A's. Ooh, I think that did something. Some more A's. Oh wait, yeah, check this out. Hello, echo server. You can see that it's working. Man, this is cool. Whatever I type into it, it responds back, which is really sick. I'm going to go into the driver and disable this hex. Oh shoot! I'm going to disable this hex dump. We don't need any of these things at the moment. All right, bound connection. Yeah, that's working. Isn't that sick? that's cool. I don't have my soundboard fired up. This would be a good time to launch some air horns or something. Maybe I can get that going real quick. All right, slowly bring up the volume. Shit. Got some air horns, maybe some claps. Yeah. So I'm pretty stoked on that. So now, yeah, this is cool. So we got our echo server running. So now, so this just kind of shows that the network stack is like kind of working. Like we have the OS running in a VM virtual machine, and from my developer machine, I'm able to netcat and connect to a port on the virtual machine, and actually do like a TCP session connection, and talk to this thing running over there. It's kind of cool, actually. So I'm just holding my enter key, and these log lines you can see are from the driver, actually. And it's the driver processing a packet like every time. Yeah, that's kind of cool, actually. what we're actually seeing is the transmit side. You can see that it wraps around at 16, and that's because the transmit buffer is only 16 slots long. Anyway, I'm stoked. This is huge. That's so cool. Okay. Yeah. Well, 1 second. I'm gonna get my headphones so I can actually hear the soundboard. I can't hear it. By default, it only goes to the stream. All right. Yo. All right. All right. So what's next? At this point, you should pass the echo serve test. All right. Thank you, Bakifer. Let's run the echo serve test. Okay. And then, so basically this testing script has a bunch of these like tests for various stuff. And now we're moving on. So we got this working. I'm going to comment that out for now. And then I'm just going to test echo serve. Anything else we need to patch? I needed to like patch a couple things to get things working in the tests. All right, YOLO, let's just run it. Grade lab 6. Seemed like it passed. Did not give very much information. Can I do a -V? I don't even know. Can we break it? I'm always a bit suspicious if things just pass on the first try. For example, let's break it by removing this one line that I added to this serve.ce file. So now that I deleted this line, the parent process is never going to wake up the input helper child process. And since the child process never wakes up, we're never going to process any more packets. So here's what I expect. I expect that this is going to cause the test to fail with like a timeout of some kind. It's just basically going to hang there and timeout after 30 seconds or something. Assertion error, socket, timed out. Cool. So that sort of helps confirm that it's actually working. I'm just going to run that one more time just because I like seeing that okay. Awesome. Well, that's going great. We're making great progress. We are almost done. This lab is only 13. Exercise 13 is the last one, and we pretty much just finished exercise 12. So I'm just gonna give it another quick air horn.
This is a certified hood classic. This is a certified hood classic.
Could also alter the text comparison in the test to make sure it tries to match input output. Alter text comparison in the test. Let's check it out. I didn't actually read this. What does it actually do? It in the expect. Here, send all expect. So what does this actually do? The user test match. User test. Ah, okay, I see. Change bound in the match to bound 1 or something. So I think what the bound, like, I think that bound is actually important, that it remains just a bound string. I think the way the test works is it launches the VM and monitors the output, and then when it sees this specific line, then it calls this function. But maybe this is what you're talking about. That's the negative case. Ah, you mean this. I see. What's up, Digitalized? Good to see you, my dude. We just had some awesome progress, Digitalized. We just we got the Echo server running. I'll just show you. We got the Echo server running. So the OS boots. We can connect via netcat, and we can type some stuff into it, and the network server responds back to us. Time for a 20-second break. Be right back. So yeah, we're getting scarily close to the end of this course, actually. Let's check it out. What's next? Well, first of all, I mean, next is the final exercise, which is exercise 13. But question, how did you structure your receive implementation? In particular, what do you do if the receive queue is empty and a user environment requests the next incoming packet? I did my receive as simple as possible. Where if there was no data available, we just return some kind of error code saying that there was no data available, and that's it. And so that means the user environment just gets, like, it just returns. And that kind of meant for a while we just had this crazy loop. For a long time, actually no, I think it still actually means we have this crazy loop. And so when there's no data, this thing is spinning super fast, which is maybe not very optimal, because it's like kind of spamming the driver. So that's a bit of a issue with the current implementation. We do spam the driver quite a bit, and perhaps take up quite a bit of CPU time. It's actually even worse because there's a global kernel lock, and so we are creating massive contention, or at least traffic on this lock, basically, since we're constantly doing syscall. So that's not great, but it's the simplest thing that works, and it seemed to work okay. In real life, we would probably maybe use an interrupt. I don't know, something like that. Challenge. Read about the EEPROM and write the code to load the MAC address out of the EEPROM. Modify your driver to be zero copy. Currently, packet data has to be copied from user space buffers. A zero copy driver avoids this by having user space and the E1000 share packet buffer memory directly. Yeah, maybe IRL interrupt with awake sleep. Yeah, many different approaches, including mapping the blah blah blah. Okay. Take the zero concept challenge. Take the zero copy concept all the way into lightweight IP. Change your driver to be able to send packets composed of many buffers without copying and modify lightweight IP to avoid merging the packet pieces as it does right now. Augment your system call interface to service more than one user environment. This will prove useful if there are multiple network stacks or multiple network servers, each with their own IP address, running in user mode. The received system call will need to decide which environment it needs to forward each incoming packet. Okay, this all sounds complicated. In general, I've not been doing the challenge exercises, so I just to make progress on the actual coursework. So I'm probably not going to do this right now. I don't feel that inspired on any of these things exactly. But good to know. Web server. So this is the final lab. A web server, in its simplest form, sends the contents of a file to the requesting client. We have provided skeleton code for a very simple web server. The skeleton code deals with incoming connections and parses headers. Actually, that wouldn't reduce contention or work since you can't sleep in the interrupts, maybe. Well, yeah, I mean, I think interrupts would definitely help in this scenario. I think they even talk about it, like how to actually do it. I mean, I guess actually it's just this challenge. If the queue is full, or blah blah blah, the environment and driver may spend a significant amount of cycles polling. The E1000 can generate an interrupt once it's finished with a receive descriptor, avoiding the need for polling. So yeah, it would be something along the lines of, if user space does a receive and then the driver did not have anything, we, instead of just like returning a simple error code, we deschedule that user space process. And then we also install an interrupt handler. And somehow we're going to get an interrupt when there's a new packet available. And then in our interrupt handler, we take the then we do the processing. We copy the packet buffer. Somehow we need to like store or know where it needs to go or something like that. But we basically just do all the same code that runs right here. This is the code that runs in case there's actually packet data to give to user space. We just do this, and so it's basically just like mem copying. Wait, this is receive. Yeah, mem copying it into the user buffer. Maybe bumping the tail, I suppose. And then we just make the the process runnable again, and we just make it eligible to get picked up by the scheduler, something like that. Okay. The web server is missing the code that deals with the contents of sending the contents of a file back to the client. Finish the web server by implementing send file and send data. All right, y'all, we are in the home stretch. Let's do this. So http.c. We have a nice little HTTP server here. How does it work? It does similar kind of stuff. It creates a socket, binds it, listens, and then does the accept loop, and then handle. So the XV6 book talks about this. Okay. Yeah. So handle, and then so when we get to this part, that means we have a connection. Yeah, we have like a TCP connection established and ready to be like read and written to the socket, I suppose. And how big is the buff size? 512. We read a bunch of data in there. We read it into the raw buffer. We zero out this request. Okay, we zero out the request. So we have a pointer to some. We have. This is kind of confusing. We have a locally allocated HTTP request object. We like get a pointer to it for some reason. We zero out this thing, then we start populating. Does this thing ever actually get used? No. Con-D, okay, whatever. We then populate some information. We set the socket. What's in an HTTP request? We have a socket, URL, and version string, so fairly straightforward. HTTP request parse. Time for some string parsing in C. This function creates a struct HTTP request. And if something bad happened, we send an error back. How does that work? We generate a response and then write it into the socket. Okay. Otherwise, we send a file back. That's how HTTP works in the basic form. Open the requested URL for reading. If the file does not exist, send a 404. If the file is a directory, send a 404. Set file size to the size of the file. And send data. Send data is over here. So send header, right? This. Like, I don't need to touch this. It's just, what is h header? Wait, whoa, this is a global variable alert, okay. Okay, so we just have like some statically declared headers. Okay. Okay, so where does my code go exactly? FD. So send data takes a file descriptor. So open. I see. Huh. Yo, Plebish. What's up? Long time no see. Hope you're doing well. All right, so we just need to open a file. Get its file size. Okay, so open the file. Somehow, like, okay, so this will involve some file system stuff. Stat to get the file size, and then it's kind of interesting. So each of these functions just like writes more data into the socket. So send header, send size. So it's a HTTP content length header. Buffer too small. Just writes it in, send content type. Okay, so we just send data into the socket, which is kind of nice. Like, we don't need to like compose it all into one big buffer and then send that whole thing. What we do instead is just send out pieces as we go. Maybe that's a good thing. Send header fin. Okay, sends the new lines that end the HTTP header section. And then we send the data. And how does that work? We just need to read from the file descriptor until it's empty, and copy, pass data, and write it into the socket. Something like that. And maybe there's a certain like chunk size we want to use. Like the most naive implementation would probably just be to read the entire file into a big buffer and then write that entire thing back out. Okay, we can decide how we want to do that. Okay, this is kind of fun actually. It's been a long time since I've just done some basic like C programming like this, and actually I don't even have that much experience with it exactly. So let's get started. So how to open a file? It's a great question. I literally have forgotten. Where can I find out how to open a file here? Who is a program that opens a file? The shell? The shell does not open files. So there's like, I don't think is there an open system call? It has been a hot minute. Here are the system calls. No, I think it's all IPC messages to the file system server, I believe. Yeah, it has really been a minute. Cat, do we have cat? Cat.c, yeah. Cat is a good example of a program that opens files. Here we go. Open. Okay, right. So we do have. Okay, yeah. lib.h would be the place to go to learn about what is available. Open. There we go. Close. So these are going to be useful. I'm just going to copy a screenshot. I don't know what this thing is. Okay. May 18th, 68. Right, so just for exercise, I'm just going to try to type this out instead of copy and pasting it, maybe. So first step is to open the file. Maybe I'll bring cat over here. And then I'll get this going over here. And what is f? F is the file descriptor, presumably. fd equals open rec. But like, what is the URL thing even actually? Like, what does this actually do? So URL was what, a pointer somewhere? All right, 20-second break, be right back. So, wow, those syscalls are way different than the RISC-V one. Yeah, I think they changed a lot when they revamped the course. Okay, so just from reading the code, we can see that URL points to the string that's after the string get with a space, and then while it points somewhere. That's not a space, so for the next non-space characters, they increment the pointer. And then eventually it hits something like the end of the buffer, or it hits a space. And it stops at the first invalid character. And then they just like compute the number of characters. malloc. Right. Somehow there's a malloc in this OS. I didn't write it. Malloc space for the URL. Mem move it. For some reason they use mem move a lot in this OS instead of mem copy. Mem move it into. Actually, don't check the return code of malloc. Mem move it into the buffer. Null terminate the buffer. So basically that's what it is. So if we go just to make it more concrete, so we have get. Like, how do HTTP requests work again? Like, what's an example? All right, nice. We have our example HTTP request. Oh, did not mean to do that. All right, maybe we can make it a bit smaller also. All right, so we have our HTTP request. Wow, got zoomed out, sorry. So the URL is going to be this string. Okay. So I think we need to get rid of that first forward slash, probably. Actually, also what I would just like to do is even just be able to kind of run this and just maybe have like a panic or something, but just see it, to kind of see it run. Start the web server. Point your browser at blah, 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 index.html. So just out of curiosity, how do I get a shell here again? User icode. I think I just do making. This time I'm not trying to run user icode. Does this work? This time I'm not. I'm trying just to run the shell so I can see what's on the file system. But for some reason the echo server just seems to keep running. It's like kind of God. make Kimu really should just what from EchoServe? Who is doing EchoServe stuff? Who is causing EchoServe to run? Okay, a little bit annoying. I can't just run my shell. I need to run this iCode program. That's the one. This shouldn't be necessary, but if I comment this out. Now the shell is here. That's like kind of weird. But now I can see the file system and we can see a bunch of the stuff that's there. Some programs, but it's also just some data files like message of the day and index.html. Crucially, index.html exists. Okay, cool. That's odd though, that if I enable this, it weirdly like takes over. Now it didn't do that. I don't know. So something is kind of wacky with the build system potentially. I don't know. Anyway, now it's working where I can run the shell and also the network server. Okay, cool. It's like kind of slow. Okay, anyway, so that just shows that index.html is there. So for example, I could, now if I go do this thing which they said run HTTP, what is the Knox thing again? Knox just means no graphic. I think it's like every other day. Stream issues with Makefile and JAWS. Indeed, unfortunately. Okay. So we're gonna run the HTTP server, which is going to cause this code to run. And what's gonna happen? It's going to pan. I'm just gonna make it panic here, send file. I'm just going to cause a panic here. So is it running? How would I know if it's... I guess I would need to maybe just add this, waiting for HTTP connections. So that's some text that we should see. And that text is not here. So Maybe it's net HTTPD. Weirdly, this thing just popped up right now. Okay, we're still not seeing the thing we should be seeing. It's still running. Wait a sec, what? This is just like the main Kimu command. And there's like the run helpers. Oh. The run helpers do this prep thing. And the prep thing like calls. This looks kind of complicated. It does this like weird. init-c like d test, right? It uses a test macro to trigger like this thing. Okay, for the moment, I'm just not going to bother with this. I'm just going to it's the net httpd, or where is this source file? It's in user httpd. Okay, so this is just the easier way to maybe get it working. Waiting for HTTP connection is good. So now it's listening on port 80, right? Hopefully. Or I don't know what port. How? Port 80. And then port 80 is like port forwarded in some way to the hosts. So I actually need to access this port. But theoretically, if I do that, this is gonna be crazy. The OS, okay, if I do this, the OS should panic, right? Right, I have the panic 1, 2, 3. It's installed. So if I fire this thing from my browser, it should panic the OS. I think that did it. User panic, blah 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 blah. 1, 2, 3. That's kind of cool, actually. I'm gonna go ahead and give an air horn. I mean, we didn't get anything working, but it's kind of neat that we can actually interact with the OS from like my my Google Chrome here. It's kind of cool. Okay, cool. So now at least we can, yeah. What I can also just do is okay, that like interesting that it's just like panicking now. Maybe it's because this tab is open. Let me close that tab. Okay, I think the thing was like that tab like was open in my browser, and something about it like being open was, I think, sending like retrying the request or something. So now, and that was triggering the panic. So now it's not, that tab's not there. I can also netcat and just send like a raw request myself. What does it look like again? It HTTP/1.1. This should also panic the OS, right? That's maybe a bit easier than using my web browser. And I can even be super cool and package this all up into an echo command, or echo command. So now I got this going. This boots up. I fire my thing, and it crashes. Cool. So now I'm ready to start programming. And basically the whole point of doing this was because I wasn't quite sure what was in URL. So now we can be in a nice, comfortable place to print it out, for example. Bam, URL/index.html, just like I thought. So that means we need to get rid of that initial slash. And so like the straight, like the easy thing to do would be just to add +1 here, but maybe we want to be careful. Like, what if it was just a slash that came in? Did we get any info on like the length? I don't think so. I think all we get is just this thing. So I'm going to just assert that URL is a valid pointer first off. I'm going to URL len equals dir len, just to get the length of this thing. And actually, I'm just curious. Yeah, if I fire off an empty string, it should just to confirm, it should say 0. Oh wait, no, it says 1, but that's fine. Yep. Okay, so 1 there. So what's the general flow here? If just a slash, return 4004. Otherwise, treat the rest of the string like a file name. So also, like, what does the caller do here? Ah, interesting. So I would need to do that myself, I guess. I could also assert something weird, like assert the URL point somewhere. I can assert URL len is greater than or equal to 1, for example. because I don't know, for example, maybe this is just a pointer directly to a null byte. It's like an empty string basically, which we're not really expecting here. So we can just assert that we can get a string length on it. And then we can even do something like assert that url0 equals a slash, for example. We could even go as far as doing that. Yeah, I don't know. Maybe that's going a bit too far. And like maybe that might be going a bit too far. Actually, that's more like input error handling. Actually, so I probably would not actually do this. So what kind of return code? This thing apparently returns a return code that's just completely unused. Like, maybe it would be cool if we could have a single send error point here that everything, like what if I don't really want to mess with it too much at the moment. I'll just handle things locally right now. So and error maybe send error request 404, for example. And then here we can do something like if, okay, it's just basically this thing. If not equal, go to error. So that's just some basic validation on the first character. So if we get here, we know that the string is valid, it has at least one character, and that character is a slash. And then now we can say, for example, if URL len equals 1, else, I don't know. If URL len equals, we actually just want to also just return an error in this case too. So I'll just move this up into the initial error handling. Just is not supported. Or maybe I can just make it refer to index.html. That's actually how this thing usually works, right? If you just do a slash, it should default to index.html. So maybe that's the semantics I should have here. And so in that case, I'm going to have a char URL. I don't have a, so it's URL equals, if URL len equals 1, then index.html. Otherwise, no, what am I doing? Yeah. Otherwise, it's going to be rec URL plus 1. So this is just, if we just got, and maybe I can even spool did request root equals okay, this makes it slightly more clear what's going on. So if they did request the root, then we just give them index.html. Otherwise, we give them URL plus 1, which just skips the slash. Cool. So now we are in a nice solid place to open up the URL they requested. What's up, Moose? Are you through the course content yet, or still on the last bit? I'm still on the last bit. This is actually just the very last exercise in the course, exercise 13. Yep. Okay, so FD, blah blah blah. We probably want to stat it. What's up with stat? fstat takes a file descriptor and then sets a bunch of stuff on the struct stat you give it, and then stat, this one actually just takes a file path, calls open, and then fstat. So it's just a wrapper. So we want fstat. No, actually I want this thing. I want a regular stat. Set and then I'm just going to do this. If we couldn't stat it, then that's a problem. I don't exactly know what. Probably panicking is not the best thing to do here. Probably just returning, but for the moment I'm just going to panic. And that's going to give us our struct stat, which contains the st size, which is what we want. And then at that point we are equals stat, oh no shit, stat dot size. We're just able to set it like that. Yeah. So I think, you know what, actually the URL is not right, it's file name. Oh shit, do not want to change all of these, wait, don't. Wait, file name? Another, dang. Continue to discard, continue. I don't know why this got so complicated, but all I want to do is just change. I'm just gonna do this manually. All right, wait. Okay. It's file name here. File name. Yes. So now. So now we're good. Now we have everything. We can get rid of this. And now we're ready to do send data. I mean, we could even, earlier I said reading the whole file into memory and then writing it out wasn't ideal, but maybe that's a good starting point. Maybe that's a good starting point. So in which case, what would we do? We actually don't. Wait, what? We actually. we don't receive enough information in this function. Oh, 20 seconds. All right, be right back. Actually, or do we? I mean, we don't have the file size here, but maybe we don't need it. Maybe it's just enough to have, like, I don't know, 512 or something. Is this possible? We have this. We just have like a local buffer, and I'm just gonna do my kind of bad coding. We have the. It's like this read thing. It's gonna be read file descriptor buff. You know, maybe memset buff, just for good practice. Read into buff size. Less than 0. Panic. Read failed. We're just doing a lot of panics. A good way to make sure your software crashes a lot and is not stable for users. But we're just gonna go with it. Well, it's kind of an error. It's also how many bytes were read, and so I don't know, something like fd buff error, something like that. You know, I think n bytes might be a little bit more clear. Then I'm just going to, yeah, I'm just doing the same thing. Assert error greater than equals 0. Similar thing. Maybe don't assert. 0 break. And then what? Return 0 or something. I don't know. Because like the return code is just passed along. Okay. What are some example return codes that people are passing here? Oh, what's up? What's up, Bacon? Nice to see you. People are returning -1 for an error. People are turning -1, -1, 1, so maybe that's appropriate. So maybe bytes less than 0, turn n bytes, I don't know, yeah. Error, okay, so if any of these syscalls fails, we just return that error code back. If we didn't read any data anymore, we just return. Otherwise, we just write it back out. Wait a sec, no. So so obviously the fd thing is wrong here. I need to be writing to request dot sock. fd is the file descriptor corresponding to the open file, and request has the socket. How does that look? Any opinions on this? We have just like a buffer, random buffer, and we're just using it. We read some number of bytes into the buffer. If there was an error, we stop. Otherwise, we check if nothing got read anymore. Otherwise, we also stop. Otherwise, we write into the socket the data that we just read from the file. Yeah, I don't love these while one loops. There's probably a better way to structure this, but logically, I think it's correct. And I kind of just tend to start out like that. So is that, there's a chance that might be it. Let's run it. Waiting. All right, y'all. Moment of truth. Are we ready? Are we ready for a moment of truth on this GET request? This should get the index to HTML. Yes! Check, okay, real moment of truth. Check this out. We got our operating system. Dang. How do I need to, which ports? I need to get this port again. Crazy, look at this. Bam! This file came from Joss. Yo, we got it working.
This is a certified hood classic. This is a certified hood classic. Brutal.
Check that out. The OS served a web page over the network stack using the network driver that we wrote. This is cool. We can get some other files. Message of the day, potentially. Couldn't fstat shit. Okay, well that crashed. Interesting. Let's run that one more time. It also crashed. Let's come back here. All right, so that worked. But it it worked, but it also crashed. So it did not completely work. What is going on here? It could not fstat. What couldn't you fstat? Okay, I think that was something kind of weird lingering thing in Chrome. Okay. Well, that was kind of cool that it sort of worked, but it clearly is broken still because it crashes the OS with a stat message. What is going on here? Probably a good time to have a cprintf on the file name. What in God's name is going on? What? You gotta be kidding me. How? Wait for something strange was happening there. Receive page fall from kernel mode. What? Very interesting. Trying to print, no way, trying to print the file name causes that? It would seem like that's the case. When did this function even run? Something about that makes no sense. It runs in response to handle client. Something whack. Something absolutely wacky is going on. That is the... If I get rid of... If I do a hello right here, it works. It actually did not crash the kernel. It's like, it's ready. It's something so peculiar. If I comment out that hello, the most strange thing happens. And I suspect this is something to do... some copy on write thing or something weird like that. I'm below line. Okay. I'm just going to keep that line in there for the moment. That helps things. Refresh the page. Favicon. Oh, yeah. Okay, so that's what happens here. The browser requests a bunch of stuff like the favicon. So we, yeah, we're obviously missing some error handling here. We are not checking FD. If FD less than 0, return FD, something like that. I'm just gonna do this. I mean, send file, right? Because this is... So no, we need to, for the moment we're just handling all this, so we go to error. And it's actually a bit confusing that you can have a label with the same name as a variable name. Okay, now we're just going to go to an error and 404 if we just don't get stuff. So that's going to help a lot. Unless we're just back to this peculiar kernel page fault. Okay. So now, I don't know what is up with that cprintf. That is so strange. Very strange. my guess is that it's something to do with copy on write, or the page not being paged in, or something like this. Anyway, so back to here. So now if we go to our browser, we retry, and it still works and doesn't crash the kernel. You can see some of these driver log messages coming through. We can even try to get the message of the day. That's cool. I don't, what other files were around there? New message of the day. So the new, yeah, we can like serve some files on the internet. We can get the root, we can just go there. That's pretty cool. We can look at what else is there. Lorem, this is lorem file, some script, like a script on the file system, test shell, blah blah blah. It looks like it's working to me, so I think we kind of did it. So let's try out the grading script and see what it thinks, and then I'll probably get going. Let me comment this out. Comment this in. All right, let's run it. Moment of truth. Let's go. Dang. Oh, okay. So will this fail? It was expecting a 404, but instead we served the index.html file. And maybe it's because... Oh, okay. So I guess they didn't really like that thing I implemented where I made / automatically resolve to index.html, like I thought a good web server should do. They want me to be a bit more strict, and just if did request root, go to error, and just return the 404, and then now this is just going to be this thing, just super simple. So now we can just do this, because at this point we're sure that it at least has 2 characters for the file name. Let's run that again. $30 out of 30. I think that's passing. Yep. I think we got it. That's pretty cool. That's kind of crazy. Yeah, so I'm just gonna screenshot that. But kind of did it. And with that like technically that brings us to the end of the class, end of the course. Right here, week 68. Challenge: add a simple chat server where multiple people can connect, and anything that any user types is transmitted to the other users. Okay. Sounds like a challenge. I'm not going to do that. Question: what does the web page served by Johnson's web server say? This file came from Joss, cheesy web page. That's what it says. How long approximately did it take you to do this lab? Good question. Let's see. So I've spent a good amount of time on this. I started working on the network driver in week 56. And we are finishing it now in week 68. So what is that? 68 minus 55. 69 minus 55. 14 weeks of about 2 hours a week, except for these last 3 where I did 3 hours a week. So that's going to be 14 weeks times, say, 2.5. 35 hours. Is that real? I spent 35 hours, a full work week doing this lab. No way. That's crazy. All right. Well, that's exciting. There's a web page for Lab 7. So I can type it in. But it's just for like more final projects. It's just saying for the final project, you have 2 options: do the Lab 6 or do like your own project. And I've been doing Lab 6. Thank you, Bacon. Appreciate it. Thanks for being here. Yeah. So I'm gonna call this done. Yeah. What do I do from here, guys? Like, it's been so long of just like doing this thing that I haven't had to think about like what to do for a long time. So I guess now's the point where I could work on my own OS at this point if I wanted to. Or to like really do it, I could actually go back and do some of these challenges, because they do say stuff like you need to do, like they say stuff like you need to do at least 1 challenge problem, and I have not been doing any challenges at all. So I technically could do that, but I don't really feel like it. I'm kind of tired of working with this JOS OS, to be honest. And yeah, I don't really know if I'm feeling it. So yeah, maybe we'll start on an actually custom OS pretty soon. That could be pretty cool. All right. Well, I think that's a good stopping point. I think I'll bring it to an end here. But I appreciate you all for being here. I'm gonna drop my Discord link as usual. Thank you for watching. Please feel free to subscribe or leave a comment if you want to support my channel. And I'll see you next week. Peace. Have a nice one.